Hello, week 4, physical geology students. We are going to explore this week questions of rock deformation. So, how do we take rocks and deform them, and how does the Earth do that? Because even rocks, have to deal with stress. You all know as students what stress is like, especially when there's exams coming up, things of that nature. And stress will manifest itself in various ways, what we call strain. And so there's certainly a relationship between the two. And so this week's material is really going to be exploring that relationship. And some of the results of stress, or some of the results of stress, include forms of strain called earthquakes, folding and faulting, and so forth. So let's get into it. Stress and strain are related to each other directly. Now, there are 3 types of stresses that tend to occur on rocks, or actions. Now, of course, these are the result of plate tectonic changes. So, divergent boundaries, you'll see tensional stress being applied to rocks. Convergent boundaries is compressional stress, and then at transform boundaries is primarily shear stress, although you'll get components of these as well. Strain is the reaction to stress. So you can see what they've illustrated forms of strain here, and the cracks and the disturbed nature of things. But that's the idea. So when you look at stress and strain, you can kind of think of them as 2 variables that have a direct relationship, or not necessarily direct, but they have a relationship. So let's take these 3 scenarios here. It's a typical stress and strain diagram. For a while, when you're applying stress to an object, the strain will manifest itself as elastic deformation. An elastic deformation, when you pull a rubber band and then you release, it goes back to its original shape. That's elastic deformation. Plastic deformation is when you bend something, or you apply the stress, and the strain causes it to change shape, and then it retains that shape. And then at some point, it just can't take any more stress, and it breaks. And that's what you're dealing with at scenario C. So with scenario, with all 3 of these scenarios, you're applying stress. Here you're applying applying a lot of stress, and you don't necessarily see a lot of strain going on. B, you get faulting, okay, but you still retain you relatively retain the shape of the material. And with C, you've applied plastic stress. You actually squeezed the material almost to the point of fracture. And all of these, of course, end as a fracture. Let's talk about that a little bit more here in a second. We represent all this geologic data, including examples of stress and strain, through geologic maps. And we're going to spend an entire week on maps later on. But you can see here on this map, this is a map of the Middletown Quadrangle, actually, and you can see the fault over here. And that fault is a result of stress being applied to rocks. It's a form of strain. And likewise, these are all different geologic units that should be horizontal. And if they were, you'd only see one because you'd only be looking at the top, or you'd see more because, of course, you have dissected valleys and so forth, river valleys. But you'd only have a limited. The patterns would look different. Here we have mountains and, of course, folded rock layers, which, again, the folds themselves are examples of strain created through the application of stress. But we'll talk more about geologic maps later on. So speaking of folds come in several varieties: anticlines, synclines, and monoclines, and are the result of ductile deformation or plastic deformation. Compressional forces mainly, and we describe them based on their axes and their plane and the limbs of the fold. So they can be either symmetrical or asymmetrical, or recumbent or overturned. Recumbent meaning they're laying over on their side. Overturned, they're upside down, or nearly upside down. So here's a couple of examples. Of course, this example here, this is a syncline. So it's a down warp fold. This is your textbook anticline. On this one, you've got an anticline out in the field here. And then down here is a monocline. So the monocline is like a stair-step fold. This part's horizontal, and this part's been folded. And the axis is over here. So domes and basins are other kinds of folded or upwarped or downwarped ductily deformed rocks. And of course, the whole state of Michigan is a basin. And you can tell because the Jurassic, Pennsylvania, the youngest stuff's in the middle here. But all of this has been downwarped. So basins are formed by the subsidence of an area between mountain ranges, or and so forth. They fill with sediment eventually, and it can be caused by either folding or faulting. In this case, the Michigan Basin was formed a couple 100 million years ago. Domes are often the results of compression and or igneous intrusions, or the intrusion of salt diapirs. So here's an example of a dome, the Black Hills. In the case of a dome, of course, the oldest stuff is in the middle because now you've eroded off the top of the dome. But all the materials are upworked. So faults come in several varieties as well. We have dip-slip faults, which are mainly normal and reverse. There's also thrust, which is a form of reverse fault that's really high angle. This is a thrust fault here. This is a normal fault, and you can see I've drawn arrows in for relative motion, and at least drawn one bed in, so you can see where the rock's been pulled apart this direction and this direction through tensional forces, just like you see it happening up here in this Horst and Graben structure, which, if you recall from the work last week, you online, the virtual field experience, you explored Horst and Graben's in the context of divergent boundaries in Iceland. Strike-slip faults move laterally. Now, of course, they will also have a dip to them. Typically, they aren't going to be straight up and down necessarily. But here, in this case, you can see the action of strike-slip faults and how they affect superficial features. But again, it's lateral motion, not up and down vertical motion. So when faults, of course, are created, you're breaking rock. You're taking the rock and you're brutally deforming it. And of course, when that happens, you release energy. You're applying stress to the rock, or the rock is under stress, and then it breaks. And there's a lot of energy, of course, going with it. You're taking all the energy that's been acting upon that rock through whatever forces have been applied to that rock, and eventually it overcomes the elastic limit and breaks the rock, and all that has to get released someplace. It builds up, has potential, and then is released kinetically. And that happens, of course, through seismic waves. And as you all know, I know where I'm going with this, earthquakes. Waves, of course, can be described using several important features, including the amplitude, the wavelength, the frequency, and the period. And of course, waves can be both constructive and destructive. So they can work together and they can work against each other. But the bottom line is that waves are how this energy is transferred through the Earth's interior. And in lab, we'll explore this more deeply. So when the energy is released through the elastic rebound or the surpassing of the elastic limit, either way, you increase the strain, you build up the energy, and the elastic limit is reached, and where brittle deformation occurs, and then the offset is created, which is the fault. The focus is the location of the release of the energy. Not all breaks in the rock happen suddenly. In some seismic areas, the motion along a fault is more gradual. We call that episodic tremor and slip. So there's not as much stress that builds up, not as much energy. It's a smaller amount of energy, but it does get released, and it does cause seismic waves. Now, in a big earthquake event, where you do have the large energy releases in a short amount of time, often the main shock will be preceded by foreshocks, and of course then post-seeded, if that's a word, or aftershocks will happen afterwards. And of course, the foreshocks precede the main event, and they can be a little bit of motion that occurs, but then the main event is, of course, when the bulk of that occurs, and then finally the aftershocks are actually adjustments to the strain that's been built up from the event. Sometimes they can be as big as the main shock, or nearly so. The focus is always along the fault plane, somewhere underground, and the epicenter is what we describe as the area right just above it, or directly above it on the land surface. Another name for the focus is the hypocenter. But these are important to keep distinct, because when we talk about the epicenter of an earthquake, we're talking about a location on the surface. The earthquake didn't originate from the epicenter; it actually originated from some depth. So when we describe earthquakes, we're not just describing a particular location in terms of latitude, longitude, or some other coordinate system. We're also describing something that occurred at depth. We've already talked about this a bit, but earthquakes can occur along the Wadati-Benioff zone at a subduction zone, and be a couple of 100 kilometers deep. So, or be very, very shallow. Seismic waves are propagated in two forms, primarily body waves or surface waves. Surface waves are the result of body waves that then, when they intersect with the Earth's surface, you get produced love waves and Rayleigh waves, and they behave slightly different ways. We'll get to those in a second. Oh, I put both S waves on here. Oops. Well, okay. So we'll go with it for now. S waves, you can see, are like the shaking of a rope when two people are holding it. We call them secondary or shear waves. P waves, if I were showing this to you, would be like if you spread a spring on the ground between two people and you pulled back on the spring and let it release. The waves occur as a pressure wave, or they move in the direction of motion. Rayleigh waves and love waves, of course, are where most of the destruction of earthquakes come from, and you can see how that works here. All of these work together to move through the earth, and I'm going to show you a picture of a computer model of the Japanese earthquake. Here, watch this. There's a couple other videos in here. I'll show you this video, but most of them I won't show you. You'll have to go and watch it yourself. This is the Tohoku earthquake and the arrival of surface waves. And you can see where the epicenter, and the hypocenter are located, and how the waves traveled through them. We'll be looking at the body waves. I love the sound effects. One of the things to note here is that these seismic waves travel all around the planet. I have a seismometer at school, and it picks up. It's not terribly sensitive, but it's sensitive enough to pick up earthquakes in other parts of the globe, assuming that the waves can make their way over here. Now, not all waves do, because sometimes they have to travel through the outer core, and that is a liquid, of course. So we measure earthquakes using seismograms, and this is an example of one here. Seismograms are created by seismographs which are part of seismometers that exist at seismic stations. So I put these definitions in here just to clarify some of these terms. But you can see the P wave is the first to arrive. That's the fastest of the waves, followed by the S wave, and then the surface waves come subsequent to those. And of course, this is an idealized seismogram. You'll be looking at several of these in lab. We'll be looking at how we can determine what the interior of the Earth looks like using seismic waves. So here's an example of a seismometer working in two cases, different kinds of waves occurring. P wave, well, it's actually the same wave, P wave, but you have the seismometer set up differently, and here comes the S wave. So you can see how they're recorded. It's a pretty simple device, really. You can make one of your own. It just won't be terribly sensitive. Okay, I'm not going to watch this video with you or these videos with you, but just know that there are a lot of seismic stations around the planet. Including, again, like I said, at my own school. One day I'd love to set Lord Fairfax up with one as well. But you can see where a lot of the Earth, there's a lot more seismic stations that are existed here. These are that exist on this map. These are just stations that are maintained by the IRIS consortium. All right, now we can use seismic data to figure out what's going on beneath the Earth's surface, and that's called seismic tomography, especially when you have data from thousands of earthquakes. Now, we just landed a seismometer on Mars, the InSight probe. Now, it's only one seismometer, but over time it will gather data on Mars quakes and be able to give us some insights, hence the name InSight, into what's going on in the Earth in the Martian interior. But already we have an idealized model we can use for how the Earth's interior should behave with the interaction of seismic waves. You can see a big difference in wave velocities when this energy hits the D layer, and then also the inner core. So something happens in the outer core liquid that's different. And of course, up here as well, with both P and S waves. So we can use this data to construct subsurface features like the magma chamber down below Yellowstone National Park. Here we're looking at it from the north. Or the geometry of the remnants of the Farallon plate that are diving down beneath western North America that created the Rocky Mountains. So we get a really good idea what's going on in the interior by using this. Again, I'm not going to watch this video. We measure earthquakes using magnitude and intensity. Magnitude, you've heard of Richter magnitude, maybe not have heard of moment magnitude. Richter magnitude we can measure right away, right off the seismogram, but it's not as accurate for large earthquakes as moment magnitude is. So, but the moment magnitude we have to wait till we get more data, and it can take a long time to calculate the magnitude of an earthquake using moment magnitude, because you have to know a lot of things like the amount of displacement, the area of the fault along which the displacement occurred, and then the shear modulus, or the strength of the rock. But every step on the magnitude scale is 10 times the strength of the earthquake, 32 times the energy released. Now this energy manifests itself as intensity, which we measure using the modified Mercalli scale, which is Roman numerals from 1 to 12, and it looks like this. So you can have everything from a weak earthquake to a catastrophic earthquake. And as you read these descriptions, I would go pause the presentation here and read these. Things like a 9 is, you general panic. Buildings may be shifted off foundations and so forth. Worth taking a look. But these are qualitative, not quantitative. These shake maps are produced using Mercalli intensity. And you can see these are two different earthquakes. This was the Alaskan earthquake from November 30th of 2018. And then this is the Virginia earthquake from back on August 23rd, 2011. And you can see the shake maps get up to strong or very strong, where the earthquakes were felt by people really close to the epicenter, but not as strongly further away. It gets to be very strong in the Anchorage area, maybe even moderate heavy to some extent. But that makes sense, of course. There's a much bigger earthquake in Alaska than it was, magnitude 7 versus the 5.8 in Virginia. But you'll also note that the Virginia quake, where it was felt was largely in the Piedmont region. So DC felt it. Even up into New York, they felt it better. They felt it more profoundly than we did in the Shenandoah Valley. Because the geology it's the same geology going all the way up through the Piedmont region. And of course, the mountains over here cause the energy to behave differently. Again, I'm not going to watch this video again. You go and find the regular version of the notes and check it out. But it shows you how when earthquake energy travels through the substrate, how solid bedrock behaves differently than poorly consolidated sediment, let alone wet water, saturated sand, and mud, where liquefaction can occur. And that brings us to the last topic, which is, of course, earthquakes and their associated hazards. There are, of course, places around the world where earthquakes occur. These are all plate boundaries where they occur. All the little red dots are individual earthquakes, and they do a good job of showing you where the plates are. And we expect that. You can see that even around mid-ocean ridges, you get plenty of earthquakes. But really, especially subduction zone areas, convergent boundaries, you get most of your earthquakes. There are major urban areas that have major earthquake risk. Even in the U.S., LA, all the way up to the Cascadia region in Washington. One day there'll be a big earthquake up there as well. The central U.S. and eastern U.S. aren't as high of an intensity, of course, but anywhere along the Pacific Rim is at high risk for earthquakes. But also, interestingly, Europe, especially Turkey, and then Iran, where are at high risk for earthquakes. Here in the U.S., of course, it's the West Coast. And a little bit on the East Coast, you can see the Central Virginia seismic zone. Now, this area in northwestern Ohio and this area in Oklahoma are the result of induced seismicity, human-caused earthquakes from the injection of wastewater from fracked wells. We know this is the case. This has been studied long enough to know what's going on there. And then, of course, the New Madrid seismic zone, which is a failed rift valley. The New Madrid seismic zone, 1811, had a major earthquake along it. And that's the subject of this gentleman is going to take you some of the evidence to describe what happened with that quake. And then this documentary is about 25 minutes long. I definitely would recommend you watch it. It'll talk about what happened during the earthquake and afterwards. And of course, Europe is a place where there's lots of seismic risk. You can see, especially here in Turkey, but even Greece and Italy are high seismic risk areas. And of course, some places, especially when earthquakes occur out in the oceans, tsunamis are a major hazard. I'll show you a picture of the globe here, where tsunamis places. This is kind of rough. I mean, obviously, inland India is not at risk for tsunamis, but their coastlines of these countries certainly are. Even the eastern U.S. is at risk. Um, but tsunami hazards are greatest with places where, of course, we're on the Pacific Rim again, and where you're exposed to the open ocean. And that brings us to the end of this presentation. So we'll go into more detail in lab, but if you missed lecture, then you'll have some idea of what we talked about. So anyway, I will see you in class.